Greetings, everyone! I am LG13, the captain of the Cosmograph 2 team. We are voyagers that do adventures across the galaxy, but with the mathematician twist. The rest of the team are currently in preparation for another journey, but they're excited to meet you too. And there we have another mission, a cosmic equation. It seems like we'll have to explore this and be guided by the mother function right on the planet there, f of x equals cosine x, through the vast universe of cosine functions. And each exploration corresponds to a specific step in graphing? Oh well, the Cosmograph 2 team will never back down from any challenge. Let's go! First off, this journey will start with me as I, LG13, the captain, will be facing a challenge of solving a function with a different amplitude, and you shall accompany me before you meet the rest of the team in different missions. By the way, do you know that people also call me the amplitude aviator? That's right, so trust me as I shall lead the way into these graphs. According to the findings of my last adventure, an amplitude of a function is the amount by which the graph of a function travels above and below its midline. Let's make it simple, specifically for our mother function of f of x equals cosine x. The amplitude of a cosine function is actually half the vertical distance between the highest and lowest points, which is equal to the distance between a highest point and the center line. So with all the definitions, how do we find amplitude in a function? First off, we must know that a cosine function specifically has the formula y equals a cosine b multiplied to the quantity of x minus c plus d, with each variable representing the structure of the graph. You can see a picture here showing the parts of a formula, although it is in sign, the variable representations are still the same. Being aware of this formula makes it now easier to know the parts, especially amplitude, or denoted as the variable a, that is just on the left side of cosine, although again is sign in this picture. Now let's get back to our mother function, the mother of them all, f of x equals cosine x. Let us compare this with another function in order to solve the mystery behind the amplitude solving. How about f of x equals 5 cosine x for starters? With number 5 being just the left of cosine, it is obviously seen that 5 is the amplitude of our given function, so a equals 5. You'll be able to easily solve this if you just base on the formula or the picture that was given earlier. But how about our mother function with no number before the word cosine? Actually, the amplitude is just automatically 1 in these cases, which means that the graph of the mother function stretches 1 unit away from the center. As for the other function, a equals 5, and since amplitude is equal to 5, it means it stretched 5 units from the center, reaching all the way to the line of number 5 for our graph. If we graph these functions, it would be easy for us to illustrate the amplitude because it is simply the distance of the center line, the x-axis, with the highest point of the graph. With the mother function f of x equals cosine x being the color green graph in this slide, as the amplitude is equal to 1, the highest point of the graph or the midline of the curvy line, also known as period, will end at the value of 1. This method goes the same for our other graph, f of x equals 5 cosine x, where the amplitude 5 will be shown in the graph by starting from the center line or the x-axis, then the graph will go all the way to the highest point of the graph that stops at the value of 5. And there you have it. It's so simple, right? As for this journey has finished, I will be then leaving you on to the next travel, where you'll be traveling with the Shifter Voyager. And good luck. Thank you, and see you later.
Hello, traveler. I'm the Shifter Voyager. I will be the one accompanying you when exploring the period of the cosine function. Gathering the data from other explorations, I was able to grasp what exactly the period of a graph is. The period is basically the distance among two repeating points present on the graph. Repeating points is guaranteed here, especially since it is a cosine function. You see, in cosine and sine functions, they are periodic functions. Basically, the graph or the function repeats itself in regular intervals. And by the looks of it, there is a formula we can use to get a period. It is 2 pi over the absolute value of b. Now, let's take a look at the function for our exploration. It looks like our mother function here is f of x equals cosine x. If that is the case, we can plug it in our formula, 2 pi over the absolute value of b, which would become 2 pi over the absolute value of 1, making our period here 2 pi. But let's say we change the value of our b in the mother formula. For example, we change it to f of x equals cosine 2 of x. In this case, 2 would be our b. So using the formula 2 pi over the absolute value of b, we can add our own value, 2, into the equation. 2 pi over the absolute value of b would be 2 pi over the absolute value of 2, which is equals to pi. So the period of the function of f of x equals cosine 2x is pi. See how changing the period changes the appearance? Looking at the graphs, we can see that the two are not matched. This is because changing the period of a function would change the wideness of the wave. If we increase the period, the wideness would lessen or make it compressed. If we decrease the period, the wideness would increase or make it stretch out. Let's take it up a notch. This may not be the one asked in our exploration, but it wouldn't hurt to practice. Let's focus on only finding the period. So, if we have the function f of x equals 2 cosine 1/3 x plus pi over 3 minus 1, and we are tasked to find its period, we can look at the form of cosine, which is y equals a cosine b x minus c plus d, and we can see that the section in the given that we are going to be focused on is 1/3. Plugging it in our equation mentioned earlier, 2 pi over the absolute value of b, we would get 2 pi over the absolute value of 1/3. This would equate to 6 pi. So the given period is 6 pi. Now, let us say that we are going to adjust the period section of the function. It would become g of x equals 2 cosine 1/2 x plus pi over 3 minus 1. To find the new period, we plug 1/2 to the formula, 2 pi over the absolute value of p, which will become 2 pi over the absolute value of 1/2. This equals to 4 pi. So, the period of the original function is 6 pi, and the modified function's period is 4 pi, which would mean if we plug it in a graphing calculator together, we would see that the modified function is shorter by 2 pi compared to the original function. Well, that is it for the period of the graph of cosine. You can move on to the next steps. Traveler, good luck!
I'm LG5, your cycle commander, and with a little bit of a twist, we have been presented with a challenge into decycling Cosmos. This is for you to be able to understand what we call these phase shifts in graphing trigonometric functions and how we can determine its movement horizontally with given examples. Are you ready? This is going to be fun, I promise. Imagine a waving line that goes up and down in a graph, like a heartbeat. Very simple, very steady. But that pattern can get a little push, either to the left or to the right, to be aware of where it begins. This is what we call a phase shift. Remember how cosine functions are of the form y equals a times the cosine of b times the quantity x minus c plus d? Would you like to guess where we can determine the horizontal shifting? With the value of c? Correct! The number presented in the parentheses with the x is where it is located. Now, what happens when the value of c is negative or positive? Well, when c is negative, the cosine graph moves over to the right. On the other hand, if c is positive, the starting point shifts to the left. Very easy to understand. To deepen our understanding with phase shifts, let me give you some examples, starting with g of x equals cosine of the quantity x minus 5. Compared to our mother function, f of x equals cosine of x, we can see here how the graph shifts 5 units to the right. Why? Because the value of c is negative. And with another example, g of x equals cosine of the quantity x plus 4. This time, compared to our mother function again, we can see the graph move 4 units to the left. Why? Because the number presented in the parentheses with the x is positive. With that, we are done with this challenge. I'm confident you understood phase shifts and how to determine one in the cosine function now. Are you ready for another journey? Buckle up, because my friend Shift Virtuoso is on their way to welcome you. Hope you learn more and have fun. Bye!
Hello, Cosmic Travelers! I'm Shift Virtuoso, your guide through the wonders of the vertical shift in the cosmic equation y equals a times cosine times the quantity b times the quantity x minus c plus d. Today, we'll unravel the secrets of how this magical d transforms our cosmic journey along the vertical axis. Let's dive in! First things first, what exactly is d? In our cosmic equation, d represents the vertical shift, the up or down movement of our graph. It's like setting the starting point or baseline for our cosmic wave. Imagine giving our cosmic graph a boost with a positive d. As d increases, our graph lifts upward, reaching for cosmic heights. It's like elevating our spacecraft to explore new territories above the baseline. As we can see, in this example, d is equal to positive 4, so the graph shifts 4 units upward. Now, let's reverse the cosmic flow with a negative d. As d decreases, our graph gracefully descends, exploring the depths below the baseline. As we can see here, d equals to negative 2, which means that the graph shifts 2 units downward. Here is a comparison of the graph where d has no value with the graph where d is equal to 4 and d is equal to negative 2. Now, let's put our knowledge into action. If we have the function y equals 2 times cosine times the quantity 2x minus 5 over 3 plus 3, the d value here is 3. Can you predict how the graph would look with this positive d? The graph would shift 3 units upward. And there you have it, the cosmic magic of the vertical shift d in our revised equation y equals a times cosine times the quantity b times the quantity x minus c plus d. The next member to guide you will be the mathematical modulator.
Hello and good day to you all. I'm the mathematical modulator, and today I'll show you all what will happen to a function given different amplitude and period values. Now I do believe that Miss Amplitude Aviator and Miss Voyager Shifter have shown you all the formulas for finding the amplitude and period. Now let's get on with it, shall we? Now for a little bit of recap. Cosine functions, or f of x is equal to cosine quantity of x, can also be written as y is equal to a cosine quantity of bx. And to find the amplitude, we just use the absolute value of A, while to find the period, we just use the formula 2 pi over the absolute value of B. Now let us say we have two functions. Let us say that the mother function will be f of x is equal to 5 cosine quantity of 1 over 4x, and the modified function will be f of x is equal to 2 cosine quantity of 2x. Now we input the values, use the formulas, and the mother function's amplitude will be the absolute value of 5, which will be 5. And the mother function's period will be 2 pi over the absolute value of 1 over 4, which will be 8 pi. Now, we input the values of the modified functions, use the same formulas. Now the modified function's amplitude will be the absolute value of 2, which will be 2. And now the modified function's period will be 2 pi over the absolute value of 2, which will be pi. Now of course, how can we compare if we don't have a graph? Now I will give you a second or two to compare the two graphs. Now, since the mother graph's amplitude has a higher value than that of the modified graph's amplitude, the waves are much bigger compared to the modified graph's waves. And since the modified graph's period has a lesser value than that of the modified graph's period, the waves are much wider compared to the modified graph's waves.
Remember the form y equals 8 times the cosine of open parenthesis b times the quantity x minus c close parenthesis plus d for cosine functions? Good, because we will be using it as we weave all what we have gathered in our explorations into this graph of space. Welcome, I am LB2, the graph maestro. I'll give an example for us to try. How about y equals 2 times the cosine of open parentheses 1/2 the quantity x plus 3 close parentheses minus 1. This sure is a challenge, but I will teach you how to dissect it. First, we identify a, b, c, and d. Using the form y equals 8 times the cosine of open parentheses b times the quantity x minus c close parentheses plus d, we'll get that a is equals to 2, b is equals to 1/2, c is equals to -3, and d is equals to -1. Good, now let's use these variables to find some important values. First is the amplitude. The amplitude is equals to a, which is equals to 2. The period is equals to 2 pi over b. Plug in the value of b, which is 1/2. It becomes 2 pi over 1/2, which is equals to 4 pi. The phase shift is equals to c, which is equals to -3. And the vertical shift is equals to d, which is equals to -1. Next step in graphing this function is to divide the period by 4 and add 4 tick marks to the right side of the origin, with the space in between being this value. Include the tick mark from the y-axis or x equals to 0. Meaning to say, these tick marks will be located at x equals to 0, x equals to p over 4, x equals to p over 2, x equals to 3p over 4, and x is equals to p. Our period is 4 pi, so 4 pi over 4 is equals to pi. The location of these tick marks will be located at the lines x equals to 0, x equals to pi, x equals to 2 pi, x equals to 3 pi, and x equals to 4 pi. Since we know that the mother function y is equals to cosine of x has its crest at x equals to 0, the period is the distance among two repeating points present on the graph, we can see that dividing the period into 4 will result in the next 4 points being patterned like this. The intercept of midline, trough, intercept of midline, and the next crest. Knowing this, the point at x equals to 0 will be a crest, the point at x equals to pi will be the intercept of the wave's midline, the point at x equals to 2 pi will be the trough, the point at x equals to 3 pi will be the intercept of the wave's midline, the point at x equals to 4 pi will be the next crest. Note that this is not yet considering the vertical and phase shift of the graph. We are still just molding its shape before we put it onto the graph considering these shifts. Here's what it looks like so far. The next step is to find the y values of these points using the amplitude. Using the x-axis as the midline of the graph, the crests will have the y value of a, or in our case, 2. The intercepts of the midline or the x-intercepts will have a y value of 0, and the troughs will have a y value of -a or -2. To simplify, we have the points 0, 2, pi, 0, 2 pi, -2, 3 pi, 0, and 4 pi, 2. Here's what it looks like on a graph. The last step is to consider the shifts and repeat the generated pattern to create the graph. Let's start with the phase shift. We know that the phase shift moves our graph horizontally, so we just add it to the x values of our coordinates. The phase shift is equals to -3, so 0, 2 becomes -3, 2, pi, 0 becomes pi minus 3, 0, 2 pi, -2 becomes 2 pi minus 3, -2, 3 pi, 0 becomes 3 pi minus 3, 0, 4 pi, 2 becomes 4 pi minus 3, 2. Next, the vertical shift, shifts the graph vertically, so now we add it to our y values. The vertical shift is equals to -1, so -3, 2 becomes -3, 1, pi minus 3, 0 becomes pi minus 3, -1. 2 pi minus 3, -2 becomes 2 pi minus 3, -3. 3 pi minus 3, 0 becomes 3 pi minus 3, -1. 4 pi minus 3, 2 becomes 4 pi minus 3, 1. So our final set of coordinates are -3, 1, pi minus 3, -1, 2 pi minus 3, -3, 3 pi minus 3, -1, and 4 pi minus 3, 1. Let's see how that changed on the graph. Notice that the blue dots are our original coordinates, while the red ones are the modified ones we're going to use for the graph. Now, copy this pattern to the left and the right to create our magnum opus. Here we are. May I present to you the graph of the function y equals to 2 times the cosine of open parentheses 1/2 the quantity x plus 3 close parentheses minus 1. Now that that's the knowledge you have gathered so far, compare the properties of the function y equals 2 times the cosine of open parentheses 1/2 the quantity x plus 3 close parentheses minus 1 to the mother function y is equals to cosine of x.
Phew! That sure was a hectic and long journey. Exploring the ways of cosine and learning more about graphing sure is tiring and enlightening. It was a whirlwind of an adventure, a story worth to be told in books and will last a century. As we navigate the graph of cosine and learn more about it, we are adding knowledge that is crucial for future explorations. Wrapping up this odyssey, we leave with our minds brim with new knowledge and hearts beating for more exciting explorations. We, the Cosmograph 2 team, bid you farewell, traveler.